Hello, in this video we want to define the center of mass, linear momentum, and angular momentum for a rigid body. Let's recall these concepts for a single particle and a system of particles, and we'll go from there. Consider a single particle of mass m moving with a velocity v. There is no such thing as a center of mass for just one particle, it's just itself. The linear momentum of a single particle is g is equal to its mass times its velocity. And the angular momentum of the particle about some point O, some fixed point O, or any point O, is equal to r, the position vector from O to the particle, crossed with the linear momentum of the particle, crossed with mv. Now if I had a system of particles with masses m1, m2, going on to mn, so here we have a system of n particles, I'll have some origin O and I can draw the position vector to each particle. The total mass of the system is equal to the sum of the individual masses. The position vector of the center of mass is given by RC is equal to the sum, the weighted sum of the position vectors to each particle, over the total mass. The velocity of the center of mass is just the derivative of RC, which also happens to be the weighted sum of the velocities of the individual particles. Now the linear momentum of a system of particles is the sum of the linear momenta of the constituents, which is also equal to the total mass of the system times the velocity of the center of mass. The angular momentum of the system of particles about point O is the sum of Ri minus Ro, the position vector of each particle with respect to O. Ro is 0, so I can take that out, crossed with Mi Vr. And we actually, when we studied the systems of particles, we found different expressions for the angular momentum of a system of particles, about the center of mass, for example, or about the random point P. Now, for a rigid body, the concepts are quite similar to those of systems of particles, but we don't sum over individual particles. What we do is we do a continuous sum, which is an integral over the infinitesimal particles, infinitely many infinitesimal particles that constitute the rigid body. So the total mass of the rigid body is the integral over the body, I'm calling the body B, of the differential mass. You can think of that, the differential mass. You can think of the differential mass as the mass of a differential portion of the body, Tm. The position vector of the center of mass is equal to the integral of r dm over all the body over the integral of dm, which is the mass of the body. So I can consider the body as composed of many dm's, many differential masses. And to calculate the center of mass of this body, say I have some origin here, and I can write the position vector to each one, r1, r2, r3, so on. For each particle, I will sum this quantity rdm, and then I will divide this by the total mass of the body to get the position vector of the center of mass. And I can take the derivative of that to find the velocity of the center of mass. And the linear momentum of a rigid body is just the mass of the rigid body times the velocity of the rigid body, which is also equal to the sum of the linear momenta of the individual particles or differential masses that constitute the body. We'll continue with angular momenta in the next video.